Hey everyone. In this video, I'm going to give a brief introduction to post-stratification. Okay, so the basic idea behind post-stratification is that we oftentimes want to make predictions for a population that ultimately differs from the data. Okay, so the most straightforward example is you have a survey that is not a true probability sample, not an actual representative sample of your population, but you nevertheless want to make inferences about the given population. Okay, so suppose we had a survey where we asked respondents about their vote intention for a given candidate, as well as their party identification. Okay, but now suppose that in this given sample we don't really have the right number of independents, Democrats, and Republicans, right? For example, there are more Democrats in our sample, or there are more Republicans in our sample, because the sample is not a true probability sample, because it's not representative, okay? The idea behind post-stratification is that we can, if we have knowledge about these characteristics, such as party identification, and we know in the population what the proportions should be of the number of Republicans, Democrats, and independents, like here, then we can adjust our sample estimates and re-weight them in order to match our population, in order to make predictions about the population itself. Okay? So in other words, a typical assumption that is kind of often unstated in any statistical analysis is that the inferences that we obtain from our data can be applied to other scenarios, actually tells us something about the population of interest, okay? And again, this assumption oftentimes makes sense if the data are actually a random sample from some well-defined population. But in many cases in political science research, we're working with convenience samples, right? We're working with samples that are not actually representative of the population. So to think about how can we adjust the estimates from that sample to match the population. And again, the solution is post-stratification. And there are a couple of different kind of ways of adjusting the output or adjusting the sample estimates to match the population. Okay, and the first kind of most straightforward example that we talked about or that is discussed in the textbook is just using weighted averages. Okay, so in order to in this case in our example here, if we want to estimate vote choice in the population, we can compute the population weighted average by examining the average vote choice in each of those groups, so among independents, Republicans, and Democrats, and then weight those averages according to the the population proportions of each of those cells, of each of those groups. Okay, so we know that there are 0.33 or 33% Republicans in the sample, so we weight our average vote choice for Republicans in our sample by the proportion of Republicans in the sample, and do that for every group in order to get the population weighted average. Okay, so that's a pretty straightforward idea, but obviously it gets a little bit more complicated once we not only are talking about one characteristic, such as party identification, but we want to consider party identification and age and education and income and a lot of different factors. Okay, so in order to kind of achieve the same goal, I have to move myself out of the way here for a second. In order to achieve the same goal of kind of reweighting our sample predictions and making them or adjust them to our sample, what we can do is we can also use regression prediction, right? So rather than using just sample averages, we can use basically y-hats predictions based on our regression model for each of those cells, okay, and thereby also take into account, for example, interactions between variables and so on, right? With a lot of different factors that you want to adjust for, of course, there will be a lot of interactions and a lot of different kind of cells you want to estimate. So ultimately, what is done in this literature, if you're using post-stratification, is to use Bayesian multi-level regression and post-stratification in order to basically estimate all these individual cell entries, and in order to provide kind of valid estimates of each of those outcomes across, not only party identification, but party identification interacted with age, income, and other potential characteristics that we want to adjust for in order to get our sample closer to our actual population. Okay. So of course this is kind of just a very simplified example, and we're not looking into like Bayesian multi-level regression in this course, but it nevertheless kind of helps to get an idea of the underlying approach. And as we move forward, and as you move forward, and potentially later on in future semesters, start working with Bayesian multi-level regression, then you can apply these techniques as well. Okay. So just to go through this example one more time, in R, we're going to look at one simulated data example that is also discussed in the textbook, which is focused on predicting support for Trump, again, based on a non-representative sample. All right. So here in this example, this is based on a CBS News poll that was conducted in 2016 prior to the presidential election. And that reported that among likely voters who preferred one of the two major candidates, 45% intended to vote for Donald Trump and 55% for Hillary Clinton. And of these respondents, there were 33% Republicans, 33% Democrats, 40% Republican, 27% independent. And the problem, of course, is that the percentage of Democrats is much higher than, actually in the actual population, and the percentage of independents was also higher than in the actual population. Okay. So here's a quick overview. If we look at the actual this is just now simulated data based on those proportions to kind of illustrate the underlying idea. Okay, so we have a poll with vote choice. We have a poll with vote choice and party identification. We know the sample is not representative because we know how many partisans are in, how many Republicans, Democrats, and independents are in our sample, and we know that doesn't match the population. Yet we want an estimate of vote choice in the overall population. Okay, so we know that the distribution of partisans here is not, it doesn't match the population. And if we kind of just look at the naive estimate, we have 45% support for the Republican candidate for Donald Trump. And of course, that is an underestimate because this is not a representative sample. Okay, so how can we make these adjustments? Again, if we use I have to move myself out of the way again. If we just use simple post-stratification, the idea is very simple. It's just reweighting our averages for each of those groups by the known percentages, population percentages of these respective groups. Okay, so we know that we should have about 33% Republicans, 36% Democrats, and 31% independents in our overall population from outside survey data and so on. And so we take our vote choice, our average vote choice for each of those groups, and then multiply that by the percentage of Democrats, Republicans, and independents in order to get a now adjusted prediction for the vote choice. And we see here that after adjusting for party identification, or the distribution of party identification, we get a larger percentage of Republican votes. Okay, and again, we can do this with this post-stratification. Just a second, I have to. With a linear model as well, right? So rather than computing the averages, we can create predictions for each of those categories by fitting a basic linear model, or theoretically a logistic regression, and then take our predictions based on the model, okay, and then multiply those predictions, those y-hats for Democrats, Republicans, and independents, which are in our post-strat data, by the population percentages that are known. So it's exactly the same process. The only difference is that rather than computing the averages, we're computing we're looking at predictions based on our linear model. Okay, And by doing that, we can directly get basically the same post-stratified adjusted prediction. And in addition, of course, we can take into account our measurement and estimation uncertainty based on the posterior simulation draws. Okay. Now, again, this is a very simplified example of the idea of post-stratification. We can extend this by looking at model transformations, looking at logistic regressions, for example, and most importantly, taking into account multi-level modeling to incorporate a lot of different interactions between these characteristics, such as age, education, party identification, income, and so on. And in order to be able to estimate all these interactions, what we're going to need is a Bayesian framework and Bayesian multi-level modeling to estimate predictions for each of those cells. And again, if you have a lot of factors, the number of cells that you have to estimate increases exponentially, essentially. And we can estimate those predictions using Bayesian multi-level modeling, and then again use our known distribution in the population to make predictions. For example, if we want to predict voting support across small geographic regions and so on. Okay. Again, on Canvas, I included a couple of additional readings that do exactly that, that kind of use multi-level regression to, for example, predict attitudes for smaller geographic areas in the United States. So if you're interested in either applying that or learning more about that, make sure to check out those additional readings. Okay, but for now, for our brief overview, basically just getting an idea of the underlying approach is sufficient. Okay, so I'll leave it at that. In the next video, I'm going to talk about multiple imputation.